Cool. Let's just talk about this interesting paper, which is native sparse attention, hardware aligned and natively trainable sparse attention. And this work is from DeepSeek, and I think this work is very impressive. So I just share in this reading group. And but before we start talking about this work, I just want to introduce this very interesting term, which is called the hardware lottery. So Sarah Hooker, a researcher from the Google Research, he proposed this term to describe a phenomenon that some research ideas win not because they're superior to alternatives, but because they are suited to the available hardware. And uh, one good example for this kind of hardware lottery would be exactly the neural networks. So we know that in 1980s we have all the technologies for the current modern neural networks. We have like SGD, we have convolution neural networks, and we have like the forward and backward algorithms for calculating the gradients. So we have everything about it. But neural network is not popular in that time because we do not have suitable hardware. And everything changed in 2020 where AliceNet comes out. Does AliceNet change a lot compared to the original neural networks in 1980s? No. But why does it become popular and create such kind of big impact in the research community? Because someone finds a way to leverage GPU to accelerate the calculation of neural networks. So this is a good example that uh, the neural networks, they are good algorithms, but they are never like be have such a high impact unless we find this kind of suitable hardwares. So it's very hard to imagine that every researchers, they just independently they develop algorithms and they usually do not consider the hardware. However, hardware plays a great role in the success of the algorithm, and we are just like enjoying lotteries by the hardware, and we and if our algorithm is suitable for the available hardware, then our algorithm might succeed. Otherwise, we mean that we lose this kind of hardware lottery, and we will just need to wait for the next suitable hardware that can conduct our algorithms. So this is very interesting. But whatever story it is, it shows that the hardware alignment is crucial for the success for your algorithm. So this is we will see this like examples for this such kind of belief across all this kind of paper reading here. And then we'll talk about the problem that we want to solve or the motivation of this paper. It is the sparsity of the softmax attention. Let's just briefly go through this kind of attention mechanisms. So basically, when we want to calculate maybe the output of the current token embeddings, we'll assume that we have the query of the current tokens, and we have all the previous key and value cache that we can use to calculate the attention score. And what we do is that we will just use this query and the keys to calculate the importance score or the attention score for each values, and then we'll just do such kind of linear combination of all the previous values to finally get the current output for the current token. And it's nothing it's nothing but just a linear combination of different values. And this coefficient, the attention score, highlights the importance of different values. And the paper of NSA, the native sparse attention, provide this figure. This shows the activation or the attention score after normalization. And you can see that uh, even though we have so many KB positions from ranging from 0 to 1000, only a very small part of the like key value pairs are lightened, which means that they will have very high attention score across all the possible KVs. This means that when we do this kind of linear combination, actually most of the part is just not useful. We can only, if we can reduce the calculation from such kind of useless accumulated calculation, then we will achieve uh, very high efficiency when we do such kind of source max attention. So the problem or the idea or the motivation of this paper is that we want to leverage the sparsity of softmax attention. However, current methods about sparse attention have several drawbacks. First, the first drawback is that most of them are not hardware aligned. So, for instance, some methods use clustering to cluster all the important key and value pairs, which introduce considerable computational overhead for the clustering operation. So this is one drawback, not hardware aligned. And the second drawback is most of the methods are suboptimal. For instance, some method will include an auxiliary loss to train the model to select the important KV cache during the attention calculation. And such auxiliary loss usually degrade the performance of the model. So this is the drawbacks of the current methods. And in this paper, native sparse attention, they will try to solve these two problems. And the key recipe they used to solve these two problems is called block or tile, or more specifically, blockwise operation. I will give you an example of how we can leverage such kind of blockwise operation to reduce the computational time of attention calculation. So here I gave you an example of flash attention. So the key idea is that the bottleneck of the computation for attention is not because that we do not, the matrix factor, the matrix multiplication is slow. It is because we have a bottleneck in the read and writes between levels of GPU memory. So we know that the GPU have different levels of memories. The GPU SRAM, it has the highest speed, which can be as high as 19 telebytes per second, but it only has 20 megabytes for space. And the second level is the GPU high speed bandwidth memory, which will have only 1.5 telebytes per second for the speed, but we will have much more rooms for the space. And for a traditional like attention calculation, we will first calculate, the raw attention score, which is actually the matrix multiplication of your query and the key. And after doing this kind of calculation, we will write back this raw attention score to the HBM, so the high speed bandwidth of the memory, which is quite slow actually. And this kind of operation will be repeated several times in the traditional attention calculations. So the idea of flash attention is that can we avoid such kind of write back or materialize of the attention score to the next level GPU memory? And what they do is that, we have first like just briefly introduce the I/O complexity here. So you can see that this I/O complexity is O(n) squares plus n times d. So here the n is the number of tokens and the d is the hidden dimensions of each token. So basically it means that the I/O complexity includes like we will write back the n square attention scores to the HBM, and also we will need to read the initial like n times d queries, keys, and the values to do the calculation. So this is the I/O complexity of the traditional attention calculation. And in this flash attention, they use the idea of tiling, which means that they break down the attention calculation into several blocks. It's kind of like doing blockwise matrix multiplication. So instead of doing one times matrix multiplication, we just divided the matrix into several small submatrix and then doing multiplication on these uh, sub sub submatrix. And And if you can see this is like the pseudocode for this kind of algorithm. So it's just like breaks down the key value and queries into several blocks, and then we were just doing the general attention calculation. And the key ingredient is here that we do not want to write back this kind of sorry write back this kind of attention score, which is S tile, back to the HBM. So what they do is that they invent an operator called online softmax. So this is a very clever trick that can accumulate the weighted sum of all the values without writing back the attention scores to the HBM. So this is called an online softmax. And with this kind of operations, we don't need to bother to write back the S tile, which actually have n square space. But instead, we only need to write back the intermediate accumulated values based on the previous attention calculation, which is the same size of the input k and v, which is only n times d. And here, the total time capacity of flash attention would be d squared times n squared divided by m. Here, n is still the number of tokens. D is the hidden dimensions of the token embeddings, and m is the SRAM size. I will just briefly like derive how this IO complexity goes. So like now we have like d times n like we have like d times n like bytes in total. And because we were divided like into several blocks, and we all know that this block is decided by the size, how many like the size of the SRAM, so how many bytes the SRAM can take. So we know that the block number would be d times n. So this is the total bits we have divided by the m, and we just go a big O of that. So this is the total block numbers we have, both for the query and for the key and value pairs. And we have this outer loop for the KV blocks and the inner loop for the Q blocks. So these two blocks, they always have this same like access to the so the HBM. So which means that the time complexity goes to so the IO complexity goes to d squared time n squared divided by m squared. And for each time, because we avoid materialize the attention score, we only need to write back the intermediate accumulated value, which means that we only need to write back m elements in total. So this gives you O d squared n squared divided by m IO capacity. So this is how this time capacity derived. So basically, we have two loops. Each loop takes dn divided by m times, and each time we will output m elements. So that's the time complexity. And this complexity is way more smaller than n squared, because usually d squared, so d is like the dimension of the hidden states for the token, and the d squared is usually way smaller than this size of SRAM. For instance, for GPT-2, the D is only 128, but for the size of the SRAM, it's usually go to 40 megabytes. So that's 40 times 1024 square, and that's way larger than D square. So this will gives you plenty of save on the I/O capacity when using the flash attention. So I just give you an example of how we can use the idea of hardware alignment to save our time when doing the calculation. So after doing all these kind of, let me just, so, yeah, let me just, uh, yeah. So after doing all these kind of preparation, we can finally go to our like paper, the native sparse attention, which is hardware aligned and natively trainable sparse attention. It comes from the DeepSeek. And there are three keywords in this paper. The first, sparse. The second keyword, hardware aligned, which exactly means blockwise operated. And the final keyword is trainable. Basically, it means that the neural network will select which key value pairs is important rather than using a fixed algorithm to select the key value pairs. So these are the three keywords for this paper: sparse, hardware aligned, and trainable. Let's just first see the overall structure of this paper, framework of this paper. So it includes three parts. The first part is compressed attention on the left side. The second part is selected attention in the middle. And finally, it goes to the sliding attention on the right side of the whole framework. And finally, all the attention calculations will be aggregated using a gated output, and the gating coefficients, the linear combination coefficients, will also be learned during the process. So let's just first go through this compressed attention. And as it says, the high level idea of compressed attention is that we will just combine several keys into one key, and we call it a compressed key. That's it. So this is the whole idea of compressed attention. So formally, suppose we have this function called KT, which we are just doing, the key aggregations of all the previous keys, and we also have this VT that will do a similar aggregation for the values, and our OT, the output, will be decided by the aggregated key, aggregated VT, and also the current query. And the mathematical formula will be something that looks like this. Here, the phi is a neural network, which is the main component to do the compression. It will just compress several keys into one key. And here, the L is the block length. So it means that how many keys will we compress in one time. And the D is the sliding window, and we will show later how this sliding stride works. And finally, T is the sequence length of total sequence we need to compress. And finally, this phi is multi-layer perception, which is a neural network. So I will give you an example here. Suppose we have like L equals 4. So for instance, our block length is 4. So means that we will compress 4 keys into one keys. And our sliding stride is 2. And we will have our phi, which is a neural network. They will do the compress, and then they will output the compressed key. And we have the slide size of 2, which means that next time we'll move 2 keys forward. So this is why we call it is sliding stride. We will make it 2 keys forward, and then we will compress the new keys. This makes sure that we have overlaps on our compressed keys, which means that we do not miss the informations. For instance, we will not break the sentence into the middle, and we will still have some overlap information during our compression. So this is like the mathematics for the compressed attention. And then it goes to the second part of the select attention. I want to have a quick note that this kind of select attention is highly correlated to the previous select attention. So to the previous compressed attention. Basically, they will use the compressed tokens before as the importance score for their selection. That's it. So they have compressed several tokens, and they will use these compressed tokens or the compressed key and values to help them select the key and values that they think they're important. So let's just go for it. And
Actually, before you move on, can you go back to the previous slides?
yeah, sure.
When you're doing the compression of the keys, this is
Yes.
compression of the key. Do you need to look at the values and the query?
Actually, no. So I think in their implementation, they do not need to look back to the values.
So in here, these are actually not needed, right?
Yes. So basically, it's a general form. So basically, it means that they will do some operations on the keys
Uh-huh.
and values. And actually, in this function, they do not use the value.
Okay, okay, got it.
Yeah, yeah, cool. Let's just go to the select attention. So the high level idea is that they will use the previous compressed keys and values as the important score to facilitate selection. That's it. So let's just go to the formal mathematic formations for the select attention. So we still have this function of kt and vt. Here, this time, this kt means the selection function of the previous keys and the query, and the value vt here denotes the selection function for the values. And here, the PTCMT is kind of an important score, which is calculated based on the current query and the compressed keys of the previous step. So they were just using it to give a important score for each compressed block. And the thing is that the selection block is usually larger than the compressed block. So they will aggregate all the important score of the compressed tokens inside this selected selection block to get the final score for the importance. So this is the aggregation. We are not. I will show an example to let you know how this kind of combination does. But the high level idea is that they will just aggregate all the compressed tokens belonging to this selection block to get their final importance score. And then they will use this final score to do selection. So they will select top K blocks of key and value pairs to do the future attention calculation. And finally, so this is like the concatenation. So they'll just concatenate all the selected key and values to do the attention calculation. So I will just show an example here. So suppose like our compressed block length is 4, and our stride length is still 2, and our selection block is 8, which is twice the size as a compressed block. And this formula will be something that looks like this. So basically, it will be a sum up of all the four compressed tokens 0, 1, 2, 3, and 4, and they have different weights. So the high level idea is that the compressed tokens in the middle will have higher weights than the compressed tokens on each side. So in this time, let me see. So the PT compression 0 will cover keys from 0 and to 4. So this is like this compressed token denotes. And then this CMP1, it will covers token from 2 to 6. And because it's in the middle, so basically it's in the middle, so it will have a higher weight of 2 to contribute to the final important score of the selection block. And you can keep doing that. You can keep doing that. You can keep doing the accumulation, and finally you will just get the important score for the first selection block. So that's it. The high level idea is in one sentence. They use the compressed tokens as a source to calculate the important score, and based on this score, they select the key and value pairs for attention calculation. Yeah, that's it. And this is like the select attention. And finally, we goes to the sliding attention. So this is more intuitive. So basically, it just takes the previous W key and value pairs for doing attention calculation. So basically, it takes a window that is just the neighbors of the current tokens, and then they just doing the attention calculation only on this local key and value pairs. So I think this paragraph says everything about three attention mechanisms. So the first is the compressed attention. It gives you a cross but global view of all the tokens you have. So this is like a compressed attention. And the select attention max, it gives you a more fine-grained key and value views, but only on selected parts. On parts, the model things are important. And finally, the sliding attention mask is just uh, get the most recent tokens of the current token, and then they calculate this kind of attention based on these neighborhood key and values. So that's everything about this native sparse attention. So I would,
Where is the sparsity? I still don't get where's so what's the role that sparsity is playing in this method?
yeah. So basically, the sparsity mainly is here. So
Um,
they only select these kind of green tokens here, and when calculate the attention, they will just throw away all the white tokens. So basically, they will not do so. It will not contribute to the the parameter the sum of all the attention scores at when calculating the coefficients.
I see. So let me take a look at it. So you have three branches. The first branch is basically you compress the keys and values, and you do attention to self-attention in the compressed space,
Yes,
and that's everything about the first one.
yes.
The second one, where does the selection happen?
Yeah. Let me just go back to maybe the slides here. So it comes here. So I should highlight this. So after we got this kind of important score, then it will just rank all the selection blocks based on this important score. And when calculation, they will only calculate the important score that is top K or top N.
Okay, so this is the so you have for each window you compute this attention score, and then you do this window-based weighting, and this is the window-based weighting, weighted
Yes.
sum,
Yeah.
and then you do the selection, basically rank them, and then you just select the top, I don't know, top n,
Yeah. Top N. Yeah.
and that's what you're select. So, and after selection, what do you do? You still use the attention score, which part of the attention score you're gonna use? Are you using
They
this?
will calculate a new attention score based on this selected keys and values. So
And
this
is it gonna transfer?
this mainly comes from the first compressed token. So basically, it's kind of like a free lunch, because we need to calculate the compressed tokens, and we can directly use it to do like with with very little computational overhead, we can calculate this kind of important score, and then we just use them to select these key and values, and we will calculate a new attention map based on the selected key and values.
Let's say that you have used this to select part of the keys,
Yes.
and then when you do the self-attention operation, what kind of are you gonna compute the self-attention mechanism using in the compressed space, or are you gonna do it in the original space?
In both. So we will first have so basically you can see three heads of this attention of this
Right, but I'm only talking about the second head, right? For the second head, are you gonna do it in the compressed space, or are you
or
gonna do it in the
original space.
original space? So this is the original space.
Yeah, this is in the
Okay,
original
okay,
space. Yeah.
I see, I see. And for the
And
first,
the sliding window will also goes to the original space.
okay, okay. The sliding window only look at the most recent window.
Yes.
I see, I see.
So from global to local, and they have like both fine grain and Koras grain, these kind of views here.
Mm-hmm. Okay, okay. Got it. But the sparsity, it doesn't really change too much the attention score, right? Um, yeah, you can move on. Let's see what happens next.
Yeah, sure.
Hi, Zuhao.
Yeah, sure.
I also have a question. I'm still not understand why the middle part is more important and how the factor two comes out.
Uh, so so um so the importance is like they think the middle part are important, so they assign this parameter to be two, and which is decided by actually by this parameters. So basically, you can take all the values here. So which is L equals to 4, D equals 2, and L plus equals to 8. So here we have 8, divided by 2, which is actually 4. And uh, and for this kind of PT1, so there's two ways to achieve PT1. Basically, you can achieve it by m equals 1 and n equals 1, or m equals 2 and n equals to 0. So when you're doing this kind of sum up, you will have two PT CMT1, CMP1 here. So actually, this is given by their formulas. So this is kind of handcraft rules. So they thought this should be important, and then they gave higher parameters to the middle one.
Oh, okay. Thank you.
Yeah, no problem. Yeah.
Actually, why shouldn't it be the opposite? Because you already, if you, let's say this is one of the window and this is the other window, um, and what's left? Actually, there's only three windows, right? If you do this, there's
Yes,
only
actually, the thing is like if you're using the formulas, actually they will cover the things in here, which is a little weird. But this is given by their formulas. I'm not sure why, but actually it will just if you taking like the selection block to be 8, then it will cover 12 total tail tokens in total.
Okay, but let's say that there is this 10 tokens, and then if you look at the first window, um,
Yeah, I think I partly understand your idea. So basically, because something in the middle and because the compressed token just have this kind of overlap, so this kind of things actually the middle one will have already been emphasized because of this
right,
kind of
right, that's
overlapping, right?
right,
Uh,
and further emphasize it,
yeah, and they
and
further emphasize that using this
that's kind of weird. Yeah, I know
spatial,
that.
they call it like spatial coefficient.
Okay, okay, okay. Hmm. Yeah, you can move on. Let's see how it works.
Yeah, let's see how it works. Yeah. So we have so basically we have so this is the whole picture of their framework, and we have covered two keywords for this paper. First, they develop a trainable selection method. So this is kind of a trainable selection, not fixed selection, which is like more intuitive, like it should function well because we learn it. And the second thing is that it is, it includes like the sparsity. So basically, they have this kind of selection for the key and values in the selected attention mask. So these are the two parts: sparse, trainable, and then we will go to the third part, hardware aligned. So to achieve this, they have this kind of group-centric data loading for select attention. So basically, it's mainly for select attention. For other two things, they do not have such kind of fancy implementations. And this implementation is quite close to the previously mentioned flash attention, but with some slightly difference. So the first difference is very straightforward because we select the blocks. So which means that we do not need to loop over all the key and values pairs, key and value blocks when we calculating like certain like attentions. Instead, we only need to like iterate on the select key and value blocks. So that's one part. But another part is that they change the inner loop and outer loop for calculation in the flash attention. So in the flash attention, the outer loop is the key and value pairs, but in the native sparse attention in their work, they take the key and value pairs or the key and value block iterations in the inner block, in the inner loop. And there's a reason for that. And I can give you a few time to think about why they change the loop order. Does anyone have any like thoughts for that? Okay, I think yeah, let me just uh tell you the truth. So this is because like in their algorithm, when they do the KV block selection, this kind of selection is based on your current query. So this is highly based on your current query. And think about it. If they employ a strategy that when forming such kind of queue block, the in the same queue blocks, all the same queue blocks will share the same KV blocks selections. when during the calculation. So they do a like specific arrangement when they select the queues. And if you do such kind of loop on queue first, which means that you are first fix a queue, and then because there are specific arrangement of this query formation of their blocks, all the queries in this block will have the same KV block selections, which means that they will reduce the fetching times of the KV blocks. So that's why they do this. Looping on Q blocks will reduce the KV block fetching. And I will just detail explain how they do this. So for the query block construction, for flash attention, they will just fetch the continuous queries. For instance, let's just assuming that the SRAM is 4 bytes. And for the flash attention, they will just take the queries from the same head, but continuous. For instance, like this. So it will just take the first 4 queries from the head one, and then they will just take the second half of the 4 queries of the head one. So they will take continuous queries. But for the native sparse attention, they will obtain queries across all heads, but at same token position. In this way, because they have the same token position and their algorithm uh, their algorithm will always force that if you are in the same token position for the query, then you will always select the same K and V blocks. So basically, they fetch something like this. So instead of fetching continuous queries, they fix queries across different heads, but at the same token position. So this is the queries all from token one, and then the queries from all from token two, and then go on, then go on. So by using this kind of specific query block constructions, they just reduce the times to fetching the KV blocks. We can just imagine if we do a loop, or if we do an outer loop on KV blocks instead of the queries, because in the same KV blocks it will have different queries because of the selection. It will largely increase the fetching times for the queries, which is not efficient. So that's why they implement a specific kernel for this kind of calculation, and that beats the flash attention. Yeah, so that's like the high level ideas of their implementation, how they achieve hardware alignment by this kind of specific design. And here it is, a pseudocode for their so-called group-centric loading. So basically, it has like Q group, which we are just loading the group at the token T, but with different group heads, and then they will load the pre-compute index for this group. So for this token T position, and then they will just looping on all the key and value blocks that is chosen by this index, and then do the attention calculation and do the accumulated updates with this online softmax. Finally, and then rest back. So you can see this is a slight difference, and then this makes it more suitable for their implementations. And one thing I want to notify is that this kind of operation is quite suitable for group query attentions. So basically, it means that the group query attention will just make several queries share the same key and value pairs, which actually makes this kind of implementation more efficient. And this is another benefits for doing such kind of group-centric data loading. So I think that's all about the implementation part, which is actually the hardware alignment part of this work. I will just pause a little bit to see if there are any further questions. Yeah. Yeah, if not, we can just go to the final part of the experiments of this paper. So we just briefly go through a different kind of experiments. So the first 3 experiments is mainly about like the performance of this model compared with the native sparse attention. And finally, it is experiments about the efficiency of their implementation. So in the general benchmarks, they include like several popular LLM benchmarks like MMLU, MLLU Pro, etc. And you can see that native sparse attention outperforms full attention on 8 out of 10 benchmarks, which is quite impressive. And on the left side is the training loss curve for both the native sparse attention and full attention. And we can see that native sparse attention is always a little bit have a little bit small training loss compared with the full attention. So this is like the experiment results on the general LM benchmarks. And the second benchmark is long context extraction. On the left side is their experiments of native sparse attention on the needle in a haystack task. So this task is just like they will provide you with very long context, so basically long paragraph, and then let you to find some specific information that is inside this paragraph. It's just like find because the paragraph is very long. It's just like find a needle in a haystack, and that's why this task gets its name. And you can see that for different kinds of paragraphs with lengths across 1,000 to 64,000, and with the dips for the dips per percent from 0 to 100%, it achieves 100% accuracy for the retrieval text in the needle in the haystack, um, which is a very good performance. And they also include very some query answer like tasks like document QA and multi-document QA. Also, they include the task like for the code generation, and native sparse attention also achieves remarkable performance. Even the baselines include a full attention baseline. So that's their results on the long context task. And they also have a chain of thought experiments for their native sparse attention. So basically, they supervise fine-tune both models, full attention and native sparse attention, on the reasoning trace of the math problems of Emma. And then they do like a comparison with a generation token limit of 8,000 and 16,000, and native sparse attention outperforms full attention on both situations. So this is their task results on chain of thoughts. And finally, this is a comparison of the efficiency between their implemented kernel and the Flash Attention 2 kernel. And due to because they do such kind of adaptations to their method, basically they change the loop and they do a specific arrangement of their queries, it achieves like 9 times speed up of compared to Flash Attention in the forward time, and 6 times speed up compared to Flash Attention 2 in the backward time. So these are the efficiency comparison between the Flash Attention 2.
What's the K? Is the context length?
K is the context length, yes. And
Okay.
if the context is longer, then the speed up will be more obvious
But do they
because
have
because of the
comparison?
sparsity.
Yeah, but do they have comparison in terms of accuracy when, for example, when you have very, very long context,
Yes, so
uh,
that's why they do this kind of
needle in a haystack?
needle in the haystack and the SQA and MQA and code generation tasks.
You for these days, how long is the context?
That's a good question. I may need to look back to the paper, but I think it should be quite long. I think it
Mm-hmm.
should be around like at least maybe at least 10,000, at least
Mm-hmm.
10,000. I think it should be this magnitude.
Mm-hmm.
Yeah, yeah. And the one thing I want to say is that this sparse attention is implemented in the DeepSeek v3.2. So basically, they use it in their real in the real productions. So they use this kind of mechanism in DeepSeek v3.2. Yeah, I think they saw the performance of this mechanism is quite well. It's quite good. So they use it in the production. Yeah. So I think that's all about this work, native sparse attention. And I just want to say something more about hardware-aligned algorithms. So from the previous works, we can see that hardware-aligned algorithms, they're practical to implement and they are very easy to success because they align to current hardware, and it's very easy for them to achieve remarkable improvement in the efficiency. However, such kind of hardware-centric focus may just limit the research creativity and scope. So for instance, in this sparse attention problem, because they know that GPU have this kind of uh, memory hierarchies, so they choose this kind of block operations. But what about other operations? So some paper they use the clustering-based method. What if we have some hardwares that is suitable for doing clustering? Would they have like similar performance compared to the only GPU implementation of this work? We don't know. So let's go back to the topic of hardware lottery. Sometimes we cannot fairly compare two baselines just because we have different development of our hardwares. So does it good or not? We don't know. I just leave this as maybe some future discussion topics. So it's just a question that are we merely building laders to the moon, which means that are we just trying to achieve some reachable goals instead of some really transformative projects. So we just limit our scope maybe to some current work, but not the breakthrough ones. So this is just just my own opinions and or some discussions about this kind of hardware-aligned algorithm. So to summarize, in this paper, native sparse attention, it leveraged the sparsity in softmax attention, and to achieve this goal, they develop a hardware-aligned design which is both efficient and practical to implement. And the experiments shows that such kind of design have a high efficiency with preserved performance. So that's all about today's presentation. Thank you, and if any questions.